Welcome to Bookish Dives. This is where we crack open some of the most influential books out there and really pull them apart to get to the core insights.
And we've done a few of these now.
We have. And today, we're tackling an absolute giant. A book that, and I don't think this is an overstatement, really changed how we understand life itself.
It's a huge one. We're talking about Richard Dawkins' The Selfish Gene. And our mission really is to get to the heart of its argument, looking especially at some of the material from the 40th anniversary edition.
Because its central idea is, on the surface, very simple, but it's also, I think, one of the most misunderstood ideas in modern science.
It really is. And let's just get this out of the way right at the top. The word you need to focus on in that title is gene. It is not selfish.
Right.
He wrote the book, in large part, to correct this really pervasive misunderstanding of Darwinism, this idea of group selection.
The idea that animals do things for the good of the species.
Exactly. That an individual animal might sacrifice itself for the good of the group. The gene's eye view just completely rejects that.
So that's what we're going to do. We're going to unpack why the gene has to be the unit of selection, what that means for things we see like altruism, and then how this idea actually goes way beyond biology. Okay, so let's dig in. We tend to think of evolution as, survival of the fittest individual, or the fittest species. But Dawkins just throws that out. He says individuals, groups, species, they're all too big and too temporary to be what's actually getting selected.
You have to take a step back. Before life even existed, the universe was just filled with, well, stable things.
Like a mountain.
Like the Matterhorn, right. It's a stable collection of atoms that resists falling apart. Or a soap bubble. It finds a stable shape. Evolution, at its most basic, is just stable things being selected over unstable things.
And once life gets going, the truly stable thing isn't the body. It's the information that builds the body.
Precisely. This is where we need to get into a couple of key terms he uses, replicators and vehicles.
Yes.
The replicator is the thing that actually survives, or doesn't, over huge stretches of time. It's potentially immortal. In our case, that's the gene, the DNA molecule.
And the vehicle.
That's us, our bodies. We are, and this is his phrase, robot vehicles blindly programmed to preserve the selfish molecules known as genes.
That's a pretty intense way to put it.
It is. But think about it from a longevity perspective. Your unique combination of chromosomes, it lasts for one generation. Then sexual reproduction shuffles the deck, and that specific combination is gone forever. It's temporary.
But a single gene, a small bit of that code, can get passed down intact.
It can travel for thousands, even millions of generations. It has longevity. That's what makes it the fundamental unit.
This is where the language gets a little tricky, because the book often talks about genes as if they're making decisions, as if they can see the future.
And that's just a rhetorical shortcut. It's a useful way to think about it. Genes obviously have no consciousness, no foresight. They just are.
So when he uses an analogy like a lifeguard, figuring out the fastest path to a drowning swimmer, running on the sand, then swimming.
He's not saying a gene calculates that. He's saying that any gene that happens to build a brain that's good at making that kind of calculation is a gene that's more likely to survive and get passed on. It's a way of thinking that helps us find the right answer.
So if every gene is just out for itself, how do you end up with something as complex and cooperative as a human body? I mean, everything has to work together.
It does. And that doesn't actually violate the selfish gene idea. Selection favors what he calls gangs of mutually compatible genes.
Like a rowing crew.
That's the perfect analogy he uses. You don't just select the strongest rower. You select the rower who works best with the rest of the crew, who pulls in time. A gene for a super efficient liver helps all the other genes in that body, so it gets favored.
So cooperation is just the best selfish strategy for the group of genes in one body.
For the most part, yes. But, and this is fascinating, there's also conflict inside the genome. You have things called outlaw genes or ultra-selfish genes, things like meiotic drive genes.
And what do?
They basically cheat. They ensure they get into more than 50% of the sperm or eggs, even if it harms the organism as a whole. They are so good at copying themselves that they can get away with being destructive. It's like a little bit of treachery happening at the microscopic level.
Okay, that internal conflict makes sense. But this brings us to what feels like the biggest challenge to the whole theory. Altruism. A mother sacrificing for her child, a worker bee dying for the hive. That just seems to fly in the face of a selfish rule.
It seems to. But what we see as altruism is often, from the gene's perspective, selfishness in disguise.
And this is where the idea of kin selection comes in.
Yes, this is building on the work of W.D. Hamilton. The logic is just pure genetic math. Close relatives have a higher than average chance of carrying the exact same genes as you.
So a gene that makes you help your brother or sister.
It's actually helping a potential copy of itself. The rule is that an altruistic act is favored by selection if the benefit to your relative, multiplied by how closely related you are, is greater than the cost to you.
Let's get specific with that relatedness number. The book calls it R. For your own child or a full sibling, R is 1/2, right? You share 50% of your genes.
On average, yes. So a gene for save your drowning brother can spread if in the process you save, say, 3 brothers but die yourself. You've lost 1 copy of that gene in your body, but you've saved 3 other bodies that each have a 50% chance of carrying that same gene. Statistically, it's a win.
The math is just cold. It's brutal.
It is. And it leads to some really strange, counterintuitive predictions. The one that always sticks with me is the runt dilemma.
The smallest piglet in the litter. Your instinct is that it should fight for every last scrap of food to the very end.
But the gene's eye view predicts the opposite. It predicts that as soon as the investment in the runt gives less than half the benefit that the same food could give to its healthier siblings, the runt should just give up.
It should die gracefully and willingly.
Yes, because a gene sitting in that runt's body has a 50% chance of also being in each of its siblings' bodies. If its own chances are tiny, the best strategy for that gene is to have its vehicle stop wasting resources that could save multiple copies of itself in its brothers and sisters.
That's a staggering thought. A gene that literally codes for give up if you're the weakest.
It's the ultimate cost-benefit analysis.
Okay, so another question then. If the relatedness to my child and my full brother is the same, R equals 1/2, why is parental care so much more common in nature than sibling-to-sibling care?
Because there's another variable you have to add to the equation. Certainty.
Certainty.
A mother is almost 100% certain which babies are hers. She can be far less certain who her siblings are or who her siblings' offspring are. Paternal certainty can be even lower.
So it's a safer bet. A gene knows with more certainty where its copies are in a parent-child relationship.
It's all about managing risk. A gene that says, invest heavily in this known copy is going to do better than a gene that says, invest in that organism over there that might be your nephew. So that handles altruism between relatives. But what about cooperation or conflict between total strangers? To explain that, we have to move into game theory.
And the big concept here is the Evolutionarily Stable Strategy, or ESS.
Right, from the work of Maynard Smith. And ESS is basically a strategy, a behavioral rule, that once most of the population adopts it, it can't be beaten by any other strategy. It's stable against invasion.
The classic example is hawk versus dove.
Exactly. Hawks always fight hard, they escalate. Doves just posture and then retreat if the other guy gets aggressive. Now, if your population is all doves, they do okay. But a single mutant hawk would be unstoppable. It would win every single time.
So all dove is not a stable strategy.
Not at all. And what about all hawk? Well, they're constantly fighting and getting seriously injured. It's very costly. A single dove in that population would do great because it never gets hurt. It just runs away and saves its energy.
So all hawk isn't stable either. Stability is some kind of mix.
It's a stable ratio, either a mix of hawk and dove individuals or a population where every individual plays hawk some of the time and dove some of the time. But here's the kicker.
Oh.
An ESS is stable, but it's not necessarily the best outcome for the group. A conspiracy of all doves would actually have a higher average payoff. No one would ever get hurt. It's the social optimum.
But it can't last.
It can't last because it's vulnerable to internal treachery. One single selfish hawk ruins it for everyone. The ESS is the strategy that is stable against selfish betrayal from within, even if it's worse for the group as a whole.
That just perfectly hammers home why selection has to be at the level of the gene, not the group. Which leads us to cooperation between non-relatives. The iterated prisoner's dilemma. Can nice guys finish first?
That was the big question Robert Axelrod and Hamilton tested with their computer tournaments, and the answer was surprisingly yes. But only if they followed a very specific strategy.
Tit for tat.
Tit for tat. And it won because it had 3 very simple but powerful characteristics. First, it was nice.
It never cheated first. Never the first to defect.
Second, it was forgiving. This is key. If the other player defected, tit for tat would retaliate exactly once on the next move, but then it would immediately go back to cooperating.
It didn't hold a grudge.
No, and that prevents what the book calls long and damaging runs of mutual recrimination. It stops a death spiral. And third, it was not envious. It was perfectly happy for the other player to do just as well as it did. It wasn't trying to beat the other guy. It was just trying to get the highest score possible for both.
And this simple, almost moral-sounding program beat all these incredibly complex, nasty strategies.
It crushed them. And it's not just theory. The book points to this incredible real-world example. The live and let live system in the trenches of World War I.
Where British and German soldiers on the front lines would basically agree not to shoot each other.
Exactly. They faced the same opponent day after day, so it became an iterated game. They learned that if I shell your position today, you'll shell mine tomorrow. This selfish desire to just survive led to this spontaneous, unspoken system of mutual cooperation, even in the middle of a war. It was a real-life tit-for-tat.
Mm.
And that brings us to the really special case, which is us, humans. Because Dawkins argues that with us, a whole new kind of replicator came into being.
The meme. Now, that word has taken on a life of its own since the book came out.
It certainly has, but his original definition was just a unit of cultural transmission. A tune, an idea, a catchphrase, a fashion.
Things that spread from brain to brain through imitation.
Yes. Memes are to culture what genes are to biology. They are replicators that parasitize our nervous systems. And just like genes, they're selected for longevity, how fast they copy, and how accurately they copy.
And the book is the example of the meme for God.
Which is an incredibly successful meme. It has high survival value because it offers powerful psychological comfort. It answers these huge, deep questions. But the real genius, from a meme's eye view, is the companion meme that often goes with it.
The meme for faith.
The meme for faith, which is defined as blind trust without evidence. Now think about that. A meme that says, believe in me without questioning, is brilliant at ensuring its own survival. It actively discourages the kind of rational thought that might debunk it.
It's like a virus that disables the immune system.
A perfect analogy. And this is how you can get memes that directly contradict genetic imperatives. The gene for celibacy is obviously a non-starter. It would die out in one generation.
But the meme for celibacy can be very successful.
Very. Because if a person is celibate, they have more time and resources to dedicate to spreading the meme itself. Preaching, teaching, writing instead of raising kids. The meme decouples from the gene.
Which brings us to the last big idea, which really shows the power of the gene's reach. The extended phenotype.
This is the idea that a gene's effects don't stop at the skin of the organism it's inside.
So it's not just my eye color, it's things I build.
Exactly. A caddisfly larva builds a little house for itself out of stones. That stone house is just as much a product of its genes as its legs are. It's an extended phenotypic effect. Or a beaver dam. That dam is a massive feature of the landscape built by beaver genes.
And the craziest example is a parasite's genes reaching into another animal's body, like a fluke in a snail that makes the snail build a thicker shell.
That thicker shell isn't for the snail's benefit, it's for the parasite's benefit. The parasite's genes are manipulating the snail's body. The reach of the gene can be, frankly, terrifying. It can control things far outside its own vehicle.
So if we pull all of this together, that was our bookish dive into the selfish gene. The big takeaway is that this fundamental unit of life, the gene, is blind, it's automatic, it's selfish, but out of that simple, ruthless logic, you get everything.
You get the entire complex web of life. You get cooperation through kinship. You get stable strategies like tit for tat between strangers. You even get a whole new level of evolution with culture and memes. It's a framework that just helps you ask the right questions about why things are the way they are.
But the book ends on a really important, I think, hopeful note. Just because we're built by selfish genes doesn't mean we have to live by those values.
No, absolutely not. That's the most common misreading of the book. Dawkins is very clear. We are survival machines, but we uniquely have evolved consciousness. We have foresight.
Something the genes completely lack.
Which means we can rebel against them. We are the only creatures on Earth who can consciously rebel against the dictates of our selfish genes.
And what's the most obvious proof of that?
Our widespread use of contraception. It is a deliberate, conscious act that completely subverts the single core imperative of our genes, which is just to reproduce.
We may be robot vehicles, but we're the ones with our hands on the steering wheel now. We can choose to defy the blueprint. That might be the most amazing thing our selfish genes ever built.
I think so. The capacity to be genuinely, consciously altruistic in a way that our genes would never sanction.
Well, if you enjoyed unpacking that foundational text and the sometimes cold but always surprising logic of evolution, be sure to follow us for more deep dives into the books that shape our world.